Okay, hello again. Welcome back, and let us continue talking about non-systematic code. And one more important part, which we will need further, and accordingly, which shows nice way of implementing coding and decoding device, is matrix for encoding and for decoding processes. Yes, so basically, matrix is a convenient form to actually perform code word calculation. So the idea is that you have information block, you have matrix of coding, so coding matrix, and as a result of this multiplication, you get a code word. Code word, yes. So basically, encoding process can be described as matrix multiplication. So in order to be able to make this code word, we need to actually design this matrix in correct way. So let us see how this matrix is designed. Basically, we start with a set of equations, and please note that the first equation in this set is actually E3 rather than E1. So we start with the last control symbol equation, and at the last position is the first control symbol equation. So here we have these information symbols, and well, it's maybe better to write it in the full form. Yes, so the full form for E3 equation, well, actually, let me use black color. So E3 equation would be 0 multiplied with C1 plus 1 multiplied with C2 plus 1 multiplied with C3 plus 1 multiplied with C4. This way, you can actually see this entire matrix row completely here. Yes, so 0, 1, 1, 1. Otherwise, you have to consider that, for example, here we don't have C1, and therefore C1 is accordingly 0 in this equation. Yes. In next equation, we have C1, but we don't have C2, and accordingly C2 is at 0. And in this equation, C3 is at 0. So basically, we mark with zeros missing components of this equation from all information symbols, and with ones which are present in each equation. Yes. This is actually a transpose symbol, meaning that what we would like to have is the transposed version of this matrix, which is accordingly this matrix. Yes, 1, 0, 1, 1, and 1, 1, 0, 1. So when we design matrix, it's convenient for us to place equation as a row, but in fact, what we'd like to is actually having them as a column. This way, yes. And we are talking only about information symbols, no control symbols here. So basically, we could say that we are taking this table of syndromes. Yes. And we, how to put it? Well, basically, we skip these lines, which are control symbol lines. And what is left is our encoding matrix. Yes, if we skip this part, you can see that actually we have our encoding matrix from this table, just by skipping rows with the control symbols. Here is E1, here is E2, here is E3, and this is C1, C2, C3, C4 position of of error position in this symbol. Yes, so making this part of the matrix is not hard. Yes, you need equations or table of the vectors and syndromes, and accordingly, this is only a half of the job. The other part of this matrix is identity matrix. So we basically place this column as they are calculated. Yes, so this is E1 column, this is E2 column, this is E3 column. And we need to place them into correct positions. So in our non-systematic code, yes, first comes E1 column, which is, well, we have it here, yes, which is this column. Yes, after transpose, this row will become as a column. Then we have E2, which is this one, and then we have E3, which is this one. So we place them into places where, for non-systematic code, we have error correction symbols. Yes. What are we going to do with the remaining part of this matrix? Well, the idea is rather simple. We put their identity matrix, so diagonal matrix with elements 1, which is split into two parts, yes, because we have in the middle here E3 column, and basically this entire matrix is our encoding matrix. So during the next lecture part today, Mr. Chen will show you how we can put in this matrix in Octave and actually make error correcting code combination and even test it for the errors. So that will be on our third lecture today, on our third class. So you will have some examples how to use this matrix in software as well. So basically the idea is this matrix is encoder device. Yes. So we multiply our data block with this matrix. For example, this is our data block. Yes. We multiply this with this matrix, and don't forget that we need to actually calculate modulus too, because well, actually we are working with XOR rather than classical adding, and yes, and this way we calculate, as a result of this matrix multiplication, we'll get a row vector, which is our code word, exactly the same values which we have calculated by hands. So we can use computer to actually perform this coding and decoding process. And that's exactly how we are going to do in our course project, task 6, when we are going to estimate how error probability has changed after we applied this coding. Yes, so which will be a very interesting and nice experiment. So far we have talked about coding process. Yes, and I have promised you, sorry, I have promised you. Well, this file will be updated. I have made some edits to it, specifically some problems in schematic in the last slide, and the link I have promised you, yes, as an introduction to algebraic structures. So here you can read more about groups as well, yes, and as you can see, there are some exercises and 40 pages about the theory of the groups. Yes, you can read all these properties as well here. Yes, conditions when it's a group. So inverse elements, yes, inverse operation of the inverse elements. Yes, all the unique neutral elements which were called 0 or 1 and so forth and so on. A little bit different, well, maybe in some ways, form of presentation, but here you also have proofs. If you are interested to have more mathematical background about this coding theory, you are welcome to use this file. It's not yet uploaded the latest version in the authors, but I will upload it after this lecture ends. And here also you have about rings. Yes, so it turns out that if we are talking about next structure, which is called ring, then it's actually a specific type of a group as well. and multiplication must be associative. Both operations must be distributive, as I have mentioned before, and the order of is not really relevant. Yes. So if we also have this multiplication order, well, basically irrelevant, then the ring can be commutative, but this is not really like mandatory. This is additional property rather than a requirement to be a ring. So yes, you can read much more theory if you're interested by following this link. You're welcome to study it. But as you have already maybe noticed, it's quite a complicated mathematical background, yes? So that's why we are not really making so much focus on it. We are just mentioning that, yes, there is such a mathematic which is base for these codes, yes? And rather than studying these mathematics more in details, we are studying the codes themselves. So, okay, now we have made our code word. So we have designed this code word. Next thing we are going to do is send this code into the channel. Then because of the noise, we will have an error somewhere here. And now our task is to actually locate and correct this error by using decoder device. Yes. So we need to make decoding equations as well, which will, considering this code word, calculate syndrome for us. And well, then after we have a syndrome, it's quite simple. When we have a syndrome, we already know where is the error, and correcting that error is not really an issue. After that, we simply add a corresponding error vector to this code word. So how does the coding procedure work in general? In general, first we receive the code word, then we can consider that we calculate check symbols again. So basically the idea is, for example, consider that if this symbol has changed, then obviously if we repeat the coding procedure by calculating these equations and we have C1 changed, right? Then we would get a result that is different from what we have gotten before. So we can say that this can be E3 asterisk, E2 asterisk, and E1 asterisk. And then we just compare these two. And if there are differences, then we are sure that this is the error because, well, the idea is quite simple. We have some algorithm at the sending side which calculates control. We send our data and control to the receiver. Receiver takes data, calculates control again, and if there were no errors, these controls should be the same. However, because of the errors, these controls can be different, and accordingly, depending on how many controls are different, we are going to get our syndrome. So the idea is pretty straightforward and easy. Yes, basically, each syndrome is going to be comparison of this original control symbol, and we can say recalculated at the receiver side control symbol, yes? And if they are the same, then the result of the syndrome by XOR will be 0, yes? If they are different, the result will be 1. We do the same operation for each equation, and hence we can get any syndrome starting, any syndrome starting from 0, 0, 0 and ending with 1, 1, 1. Accordingly, any syndrome from this table. Now consider, for example, what happens if we have error in this control symbol E3. So we have this code word. I'm going to write it here. So this is our E1, E2, E3. So this is C1, C2, C3, C4. And now we have error in this position. And instead of 1, we have received 0. So this is the error, yes? What happens then? So, as you imagine, if we now take these same equations, these very same equations, and calculate syndromes again, so we will have E1 with asterisk calculated by adding symbols C1, C2, C4. None of these symbols have been changed by error, so basically we are going to get, so C1 is 1, C2 is 1, C4 is 1. Wait, so all of our, sorry, I have mistyped our information part. It is 0, 1, 0, yes, this one. Because it doesn't matter, because for 1, 1, 1, we would get different E symbols, and then I would be unaware what went wrong, where have I made an error. So it's important to actually match control symbols and information symbols. So okay, now C1 is 1, C2 is 0, and C4 is 0. So E1 should be, yes, 1. Now we calculate E2 with asterisk. Then again, none of the control of the information symbols have been changed, so it will be the same as received. Yes, it will also be 0. Now, however, when we calculate E3, yes, by using this equation, we'll get C2 is 0, C3 is 1, C4 is 0, which gives us 1, and we can already see that E3 is different. So syndrome 1 is actually E3. What we have received is this 0, plus E3 what we have calculated again, which is 1. S2 is the same operation for second control symbol, which will give us 0 because it's not different, it's the same. And S3, accordingly, the same procedure for E1, which will give us 0. So the syndrome is 1, 0, 0. And if we look in our table, it indeed matches the error in the symbol E3. So we have found this error correctly. So to summarize, what we do is we perform the same algorithm again at the receiving side and compare results, what we have calculated, with what have been provided in the code word by transmitter in the place of the control symbols. If these symbols are the same, we don't have error. If, however, there are differences, then there are errors. So what we are going to do now is just substitute this symbol. No, sorry. So with asterisk, we have denoted the symbol we have received. So this is one we have received. And this is one which we calculate again, anew. So what we are going to do now is to actually substitute equation for this symbol of information symbols into this equation. And we get decoding equation set. Yes, so basically, instead of this E3, we have now put the entire equation, accordingly marking with asterisks, because these C symbols could potentially contain errors as well. Yes, so we denote with this asterisk that this is not a reliable symbol. Yes, we don't know, does it have error or does it not? And of course, naturally, we can have more than one error as well, because we selected our code to correct one error. However, channel is, well, not really required to oblige with that choice of ours, and it can still produce more than one error in the code word. And in fact, you have calculated in your course project the probability of such condition, which was task 8, last task. What is the probability of having more than one error in your channel with your modulation type? But okay, I a little bit digress. So now we have calculated the syndrome from our code word, for example, yes. And then, assuming that we have found the syndrome, in our particular case, we have found this syndrome, for example, we know the exact error vector, which we need to add to our code word. So here is our code word. It has error in this position, yes, because, well, we put on all everything, yes, inside. So E3 is 1, E2 is 0, E1 is 1. Then we put C2, C1. Well, basically fill in this equation with real data from this code word. Sorry, I was writing below, but this is incorrect. Actually, it was here. Calculate the syndrome. The syndrome is 110, which is in binary or in decimal form 6. Yes, so we know that the error is in the 6th position, and we add error vector matching this syndrome. So as you can see, indeed, for this syndrome, we have this error vector. And that is how we correct the error. Now, if we are checking this code word, so C3 symbol now is 0. So wait a minute, C3. So C1 is 1. Okay. Yes. Yes. No, wait a minute. Don't really understand. So C1 is 1. Well. Yes. It's a little bit different. So this is not error. So this is our original code word. This is how error is introduced, and this is with error. I was just a little bit confused as to why do we have C3 here as 0 rather than 1, because 1 is actually correct code word, yes. So we add error here, and we get this symbol, well, basically changed, yes, altered. And accordingly, this is the error. So if we calculate the syndrome, then it shows us that the error is in symbol C3, which is true. Yes, because here is symbol C3. So that's how we have found, and accordingly, how we can correct that error. So, similarly, we can make a decoding matrix. However, it's much easier to make, because what you need to do is actually take this entire syndrome matrix, and that's basically the matrix which you need for syndrome calculation. Yes, so it's just this matrix, yes, and that's enough to actually multiply your code word. Don't forget to use modulus 2, because this multiplication of matrices uses classical addition. Yes, so we basically add well, basically for the first column of this one, let us calculate it manually. So we have this 1 multiplied with 0 plus 0 multiplied with 0 usual matrix multiplication, yes? 1 multiplied with 0 plus 1 multiplied with 1 plus 0 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 multiplied. Well, in this particular case, okay, it's strict 1 and it's okay, yes. However, for the second column, no, for the third column, yes, we can see that if we would multiply this and these, add them together, that would give us actually 2. Yes, so that's why we need this reminder after division to get the here 0, yes, because normally this is not XOR, this is normal addition, which can produce 2, 3, and so on. Yes, so for that reason, we need to be aware of that fact in computer software and perform this conversion to XOR operation. We could have written our own procedure for matrix calculation with XOR basic operation, but well, since XOR is so easily modeled by this reminder operation, by this modulus, we don't really have to. We can calculate this as usual addition, and the result is then converted by using modulus 2. So the calculation of the syndrome is pretty straightforward. You take your code word, you multiply it with this matrix, and you get a syndrome. Yes, the syndrome is 6. So let us talk a little bit more about systematic code. What will change in that particular case? The equations are exactly the same, so I'm not going through them again. Yes, so you still make equations by writing this table. Well, actually, I said I will not go through, but I will recap it fast. Yes, then you prepare each equation by reading the column. Select which symbols should be control symbols. Yes, and have these coding equations. Next, you make decoding equations based on your coding equations by simply adding to them this control symbol and setting result equal to syndrome. Yes, and these are exactly the same equations. The only difference is that your code word is organized a little bit differently. Yes, so basically you put all the control symbols in last positions. That is all the difference. Yes, so in paper, when you write your tasks, you will nevertheless generate the equations in the same way, regardless if it's systematic or not systematic, but you will write down your resulting code words in systematic or non-systematic form. So this is basically the matter of arranging symbols, nothing more. So, however, this has some consequences. First of all, no longer syndrome will be pointing directly to the symbol position where we have errors, because lastly here we had error in the 6th symbol and the syndrome was exactly 6. This was as a result of this non-systematic approach. Yes, if we convert it into systematic, then our code word will be rather this. Yes, 1, 0, 0, 0. Here we are going to have error. Yes, and here are our control symbols. Sorry, 1, 0, 1. Yes, and accordingly, so here we have 0, and accordingly, this number 6 no longer points to correct position because now we have error in the symbol number 3. Yes, so this property that syndrome by its value shows us directly where is the error works only for non-systematic code. For systematic code, you will have to take that into consideration and search for correct error vector. Furthermore, encoding and decoding matrix as well must be rearranged. Yes, and in the schematic, well, basically what changes is where each cable goes. Yes, we'll get to schematics right now as well. Furthermore, Mr. Chen will show you even more during the third part of our lectures today. So how do we change the systematic or non-systematic matrix approach? So basically, we just rearrange the columns in accordance with a new order of symbols. So here we have our control symbol columns, and here we have them in new order, yes? So basically, we just replace some columns, change order of these columns, and that's it. That's for encoding matrix. And here you can see in clear way the identity matrix, so-called I matrix, yes, which simply copies your data symbol. Yes, this is needed to actually, when you perform multiplication, keep your old information symbols as a part of the vector, and all of these are calculated accordingly by linear superposition of these information bits. For decoding matrix, we also do the same thing. We rearrange rows. Yes, so here we had E1 row, E2 row, and E3 row. Now they are located at the end of the matrix. Because in your code word, this data is also located at the end. So in order to get correct syndrome, you need to remake this matrix. Yes. Another approach would be before matrix multiplication, you actually rewrite the code word itself into a new form and then perform operation with that. It's well, often done so, but well, it's not really mandatory. So as I said, it's much more beneficial for us to use non-systematic approach. However, systematic approach can be more convenient to read data. Yes, because here you need to actually read from the correct places. Well, each of the methods has its own strong sides and weak sides, as you imagine, but anyway, hopefully that explains you the difference, and the difference in designing equations is really none. Yes, you design the same equations for both cases. So let us talk about schematic diagram, which you will need to draw for your course project. And I have also uploaded some guidelines to Ortus. Well, maybe actually we should look at them now. Wait a minute, it's not you yet. So all these guidelines are available in here in course project part. Yes, so you can, for example, open this PDF and step by step by using KiCad software, you can see how this schematic is designed. Yes, so to speak. Now I will explain to you the logics and approach, and you can repeat that process yourself. You are not obliged to use exactly this software. You are not even obliged to draw it on computer. You can maybe draw it on paper and then take a scan or photo of that schematic. It's whichever way is more convenient for you to actually make this task. Yes. So, okay, what is the logical structure of our encoding device? So, first of all, we need some memory where we are going to store our information bits. So, info goes to memory. Then we need some logic, XOR logic, to implement encoding equations. Yes, to calculate this control symbols. And accordingly, we need output memory to store our code word, where it will be read from, code word. So this is quite simple approach. For XOR elements, we are going to use accordingly XOR components. Yes. Logical elements. And for registers, for memory, we are going to use registers, parallel registers to read data and write data. Yes. So let us start with these equations, yes, which we will need to implement. Once again, these equations have to be first obtained before you can draw schematic, which is naturally. These are for example of 7.4 code. So here is the register, yes, for the input. So our input has 4 information bits, and the registers, if you look the software, well, Mr. Chen will show you more specific in software how to draw. I wanted to do that now, but then I realized I might take more time, and accordingly, well, in the next third today lecture, you will get more. But the long story short, yes, is that these registers can be in different number of input lines. There can be 4 inputs, there can be 8 inputs, and probably even 16. I'm not really sure about it. Not in all software you can find, but you need to accordingly know what is your K. So for example, if you have M equal 31, then K would be 25, or 26, I'm sorry, and you accordingly would need to have 26 input lines, which you can combine from these. For example, you can use 3 by 8 and plus 1 by 4, and you will still have extra 2 lines unused, yes, which you will just show that you have nothing connected to them, and that's it, yes. So it's not really mandatory for you to follow these specific sizes. However, I do recommend to actually study this topic and draw correct elements, which can be found as physically existing microchips, yes, because you can always, of course, draw one big register with 30 inputs. However, such are not exactly produced, yes. Well, no matter. If you find it too difficult to actually follow these correct dimensions, correct inputs, it's okay to draw in more general way. You can use, for example, Paint software or some other to make your custom block with specific number of inputs which you need. But I still recommend you to spend extra time and get better knowledge of making schematics. Yes. So here, then, this is the input register. Now, this is called a bus. This is a so-called thick cable with multiple wires inside it. And I connect this bus to the outputs of this register, number the outputs, and accordingly I can connect to this bus from any other points by specifying cable number. So, for example, if I want to make a control symbol E1, I need to add together C1, C2, and C4. C2 is second line, C3 is third line, C4 is fourth line, and C1 is first line. So you can see here that I have added actually here C2 and C4. Yes, and here I add that all. So basically what I have here is C2 plus C4 plus C1, and I get this error correction bit E1. Yes, here you can see 1. Also, here is the ground 0. Yes, if I will have some extra elements which I don't need, I will then accordingly use this 0 input to, well, leave result unchanged. I have 2 microchips with XOR element. Yes, each of these microchips has so here we have 8, 12, 16 terminals. Yes, 8 here and 8 here, and 4 XOR elements inside it. Yes, I'm not numbering specific inputs and outputs of this microchip because it's too detailed schematic. You are not obliged to draw that. But you need to realize that once we place this component, well, it's best for us to utilize it to the full extent but still you will see that in my particular case, these two components are too much. However, one is insufficient. Yes, so I will have some inputs unused, and well, that sometimes is unavoidable, what I can say, yes. But anyway, I try to show you in this schematic as close to real elements as possible, yes. Once again, you are not obliged to do the same way. You can always, for example, make 3 inputs XOR if you draw this on paper, yes, or 4 inputs or 6 inputs, whatever you need, and accordingly connect them to the corresponding outputs of this register. Same way, we make the second equation. Yes, so basically here we add C1, C3, and C4. And also to use this extra input, it's not recommended to leave it unconnected, yes. So I connect it to ground, which is extra 0. So basically my equation is sooner rather looking like this. Well, this 0 doesn't change anything, yes. So it's still valid logic. And here I need to actually add them up together. Yes, so basically the logic here I use is like C1 plus C3 plus C4 plus 0. Yes, and we get symbol E2. And the last equation accordingly adds together C2, C3, and C4. Yes, this produces us the third error correction symbol. And these we do not really need. Yes, so I connect inputs to 0, to ground, and I leave output unconnected. Yes, here you can see the memory for the output. I'm using here double 4-bit registers. Yes, each of them is a separate microchip. They are not in same case, let us say so. Yes, of course you could have used here one with 8 outputs. It's also okay. Yes, I just wanted to show you how you can combine multiple smaller registers in this way. So what we do next is we actually connect our information bits into correct positions. So now I have non-systematic code. So I need to put C1 at the position at the 3rd position, yes, C2 at the 5th position, C3 at the 6th, and C4 at the 7th position. Now this input is also unused, so I connect it to ground with 0, and I don't connect this output anywhere. And accordingly, the same way, we put control symbols E1, E2, and E3. Now, if you would have systematic code, then you would accordingly connect differently. So first you would connect these 1, 2, 3, and 4. Well, let me see. We don't have. Well, Mr. Chen will show you that in next lecture too. But what matters most is that this is actually when you have difference in your schematic. If you have systematic or non-systematic code, you just simply connect these wires a little bit differently, and that's basically all the difference. Yes. So for decoder part, it's a little bit more tricky because in addition to calculating the equations, we need to perform the correction. So basically this part is similar: memory for input, memory for output, equations logic with XOR, and correction. So for correction, we are going to use a specific component called line decoder. Yes, line decoder, which will convert our syndrome into correction signal, which will be added to actually make a correction of the error. So we need a set of decoding equations, which are the same for systematic or non-systematic code. Memory now at the input is M elements, and at the output will be K, which is 4. Yes, and here we have 7 because we need both control symbols and information symbols. Likewise, as before, we calculate 3 syndromes, yes, by implementing these equations in a very similar way as you did so for coding. So this gives us the syndrome. Now we need output here, register, but we also need an option to actually correct any of these output symbols. We don't correct any of E symbols. If error has happened in those control symbols, we just will discard them because they don't contain user information. User information is contained in this message, yes? So we have to change error if error is happening here. If the error is happening in some control symbols, we know about it, but we don't need to actually do anything about it. So the correction is going to be applied by having this XOR input. For example, here, third component, yes, third line is actually C1. Yes, so C1 is third. So we send C1 through this XOR, and the second input can have either 0 or 1. If it has 0, then this symbol is left unchanged. If it is 1, then the symbol will be inverted, effectively correcting the error. Yes, so what we need to do now is convert this syndrome into symbol 1 sent to correct position to here, to here, to here, or to here. And for that reason, we are going to use a component called line decoder. Now, this is denoted like this. It has, in my particular case, it is 3 by 8 lines, but there exist also 2 by 4, 1 by 2, 4 by 10, and 4 by 16, which are physically existing microchips. Now you may say that you will, for example, have 31M, so you will need to combine multiple of them. I will show you next slide how to do that as well. However, next slide contains some error, so I will probably show you in another program it. I haven't just figured out how to make a picture with transparent background, but okay, I'll explain later. So how does this line decoder work? It works very simple way. Consider that, for example, you are sending here 0, 0, 0 syndrome, yes? In that case, it will produce symbol 1 at the output matching the decimal form of this number. So I have sent 0, 0, 0. Decimal form of this number is 0. So output 0 will produce 1. Now, if I send, for example, 1, 0, 0, that would be, so depending on what was, this was S3, so this is actually in decimal form 1. Yes, this is least significant bit, this is the most significant bit. S3 is least significant, S1 is most significant. So this will produce symbol 1 at this output, which is control symbol E1, and we don't need to do anything about it. Now, if we have 1, 1, 0, which is 3, where is C1 located? If the syndrome will be this syndrome, yes, then this will produce symbol 1 at this output, which will go here by XOR and invert C1. So basically here we'll have C1 inverted, and here we'll have C1 original. And well, this can happen only in one case. If we know that C1 has the error, which means that it has already been inverted once in channel. So double inversion returns correct version of C1, and that's how this error is corrected. And all the other outputs at the same time will produce 0, so nothing else will be changed. So if we have error, then according output will produce extra 1, which is correction signal, and this correction signal will actually change that problematic symbol, which has error, into correct one. So that's how it's working. Yes, if we have systematic code, again, all the difference is just these numbers. Yes, how the symbols are arranged, nothing more. We are still considering with this component that our, well, basically with all this part, yes, that our code is non-systematic, because this line decoder actually expects to find symbols in their non-systematic positions. Like this is, well, nothing. This is E1, this is E2, C1, E3, C2, and so forth, meaning in non-systematic order. Even you have systematic code, you still have to consider that here we have non-systematic version. Yes, and connect wires correctly. So, and finally, what happens if you need larger line decoder than you can have? Here I have, for example, made this 3 to 8 line decoder by using double 2 by 4 decoders. Yes. Please note, however, that it has inverse outputs. Yes. And accordingly, here I also added an inversion to compensate for this inversion. Yes. So that's how it's working. The trick is that each of these line decoders has enable input. So if we send signal to this enable input, it's working. If we don't send, it's accordingly turned off. And this way we can actually choose which of these we enable by using yet another line decoder here. So we send syndromes S3 and S2 to both of these. Yes, these are accordingly, well, if I write down all my syndromes, then it's from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Yes. So this is S2, this is S3, and this is S1. So you can see that in these two halves, we have exactly same content, let us say so. Yes, all the difference is this S1. Accordingly, this S1 turns on either first decoder or the second decoder. If the first decoder is turned on, then we are working from 0 to third output. Yes, so this is 0, 1, 2, 3, 4, 5, 6, and 7. Yes, if S1 is 1, then this enables the second one. Yes, and accordingly, this will give us 4, 5, 6, or 7th position. Yes, so the trick is to send this symbol. It's either 1 or 0. If it's 0, then it enables this decoder. If it's 1, that enables this decoder. And you can sell even more of them. Yes. For example, if you would have 4 syndromes, syndrome S1, S2, S3, and S4, then again, you can send here S3, S4, and 2 of the first ones, S2 and S1, can be sent here, and accordingly you will have 2 more of these line decoders working up to 16. That would be total numbers. Yes, and the error I was talking about here is that I have incorrectly connected these lines. So the correct connection would be this way. Yes, because here we have no errors. No errors. Here we have E1, E2, which are not connected, E3, 3, which is not connected, then C1, C2, C3, and C4. In PowerPoint presentation, I have a little bit shifted it. Yes, I haven't considered that this Q0 is actually no errors rather than error in the first. So this is my mistake. I will find a way to make this picture transparent and upload correct version into Ortus along with that new link. So, do you have any questions for this material which we have discussed today? Because on third lecture, you will Mr. Chen will show you more examples of course project, how to draw these schematics, how to use matrix to calculate syndrome, to calculate code word, yes, and you will be able to, for those of you who have group code, you will be able to start working on that part of your course project after this lecture. So no questions yet. I'm not going today anywhere. So if you will have questions, I will be glad to answer them. But after the short break, Mr. Chen will take over and we can start, well, at well, let us start exactly at 11. Yes, we'll have a little bit longer break because we have been studying a lot today and some difficult material. So let us take a good break before practical part. So at 11 o'clock, Mr. Chen will be waiting for you here. And for if anything else, wish you a nice weekend and thank you for attention.
Thank you.